Meet Pete. Pete doesn't know it yet, but in 3 hours and 41 minutes at 7:43 a.m., he will be rushing his pregnant wife Abby to the hospital. He won't be thinking about whether his car is charged and able to safely cover the distance from here to there, because the engineers who designed and built Pete's car already thought all about it. SAE International assembled a team of engineers from all over the world to think systematically about the charging of Pete's car. These engineers developed a series of standards that made mass production of Pete's car safe, affordable, and environmentally sustainable. But Pete won't have to think about any of that. He's probably never even heard of us. And we're fine with that. Because in helping the engineers keep Pete's car fully charged and safe, we've done our job. Sleep well, Pete.
Hello and welcome everyone. I'm Dwayne Taylor, R&D engineer with Denso International America and chairman of the SAE Interior Climate Control Steering Committee. Thank you for joining us today and to the Detroit section for hosting this event. Before we start, I want to address a couple of housekeeping items. All are muted with camera off to keep the integrity of the meeting. Please do not attempt to unmute yourself or turn on your camera during the discussion out of courtesy to the speaker. We do want questions and feedback and encourage you to use the chat box function to ask any questions that you might have. If for any reason you must leave the meeting throughout, the meeting will be posted on the Detroit section's YouTube channel later. Today we're going to be hearing from Derek Redding, CEO of Defrost Technologies, about their new method for low energy surface heating available on electric vehicles for passenger cars and commercial vehicles. Derek, welcome.
Hi, Dwayne. Thank you very much, and also thank you to the SAE Detroit section. It's great to be here today. I'm also joined with me with our CTO, Sammy Sad, who's sitting next to me. Sammy, if you want to wave, maybe you can see behind me. He is a sorry, I went the wrong way with the camera. But anyway, Sammy is our CTO and co-founder. He has a PhD in surface thermodynamics, which is very topical to this discussion today. We are based in Oakville, Ontario, and just down the road from the Ford Oakville plant. All right. Can you see this? Okay. Range decreases as it gets colder or warmer, and there's been a couple of good studies over the past few years. AAA has done one, GeoTab and Recurrent. I'm showing a graph here from GeoTab that focuses on connected solutions for fleets, and they have some really good data on fleets of electric vehicles in terms of actual real-world performance of range versus temperature. And what I like about this graph is it shows specifically how actual range compares to real-world range on the left axis, and the x-axis shows temperature. So as we move away from ambient, which is around 23 degrees Celsius, you can see we get down to about 0 C. The 50th percentile range drops about 40%. And then when you get down to minus 20 C, it drops to 50%. And then on the warm end, there's also a similar drop as well, not quite as pronounced, but there's also the incline is a little bit more. And before I talk about our technology, I'd like to talk about low-E windshields. And this technology, this was originally developed in the 1970s or 80s for flat glass applications. And the idea was to try to reflect away the non-visible portion of sun energy, which most of this is in the IR, the IR range shown in the graph here on the left. And so about 48% of the sun energy is in the non-visible range. So the South Wall, which was one of the early innovators of this 40 years ago, focused on metals or materials that were transparent but would reflect the IR portions or non-visible rays while letting the visible rays penetrate through glass. And I think they were very successful in getting this, because I'll show some adoption rates of how their technology has been adopted into many applications in flat glass. And then this study from SAE on the right side shows where solar gain energy enters the vehicle, about 40% through the windshield, side glass about a quarter, and the rear is about a third of the solar gain into a vehicle. And this table here shows the performance of different metals in different coating technologies in terms of visible transmittance and also TTS, or total solar transmittance. You can see that all of these offer solutions in the visible range, or allows visible light to transfer above 70%. That is, there is a regulation for that, but you can see pretty significant reductions in total solar transmittance shown on the right side. So for example, FTO, or fluorine tin oxide, can reduce that solar transmittance from, it can bring it down to 50 to 65%, which is passed through, and double layered silver allows 50 to 55%, and then triple silver at the bottom allows 35 to 48%. And this is typically applied to surface 2 or surface 3. Most of the automotive applications are on surface 3, and there's two different coatings, and the right side over here shows the typical construction in the windshield glass. And there's a number of benefits of the low-E coatings. In summer, it reduces the energy transfer into the cabin, about 10 C lower. It also reduces surface temperature. You get shorter time to comfort. I grew up in Arizona, and probably the most difficult thing during the day was getting into the hot car late in the afternoon. And it takes a while for the air conditioning to bring the cabin temperature up, and then you have all the materials with all that latent heat that's soaked into all the materials. You also have a potential HVAC size reduction, increased driver comfort. Another important aspect too is reduced fading and degradation of materials in the vehicle. I'll also point out there was a very good study done about 10 years ago on the impact of these types of low-E glass systems on vehicle range. They looked at both gas, hybrid, and electric vehicles. I'm going to focus on the results from electric vehicles, but using a windshield that had a TTS of 55%, which was down from the baseline study of 62% for the green windshield or green glass windshield that was in it. Range improved about 1 to 1.5%, but at that time the TTS value was maybe might have been at best standard at that time. Today the TTS values are much lower. I think it'd be worth revisiting that study to update it, because I think the EV range improvement would be quite more than what they saw given the improvements in the TTS. And one example that I'd like to show, this study just came out from Alex Krasnov and was published in Optical Materials this month. This is very interesting because it shows the thermoelectrical and optical relationship using triple layered silver. You can see TTS on the left side, sheet resistance on the bottom, and then on the the third axis, you see the visibility, the amount of visible light that passes through. And you are seeing TTSs of even below 40% are being shown to be possible now. And in this case, and these are all being shown to pass through 70% of the TVIS on it. Next, I want to talk about adoption rates. In residential and commercial, we've seen just over the last, really since about 1990, it really took off. And today now, according to the Department of Energy, 85% of residential windows now have low E glass, and in commercial, that's 50%, probably tinted glass and other solar reduction technologies would probably bring that number up, but if they look just at low E, that's more than 50%. So we're starting to see a number of EVs now have low E glass, and I think we can start to ask the question, is automotive next to get this type of adoption rate of low E windshields into electric vehicles, given the strong solar gain reduction that they can offer? So now, if we think about having this transparent metal coating inside of the windshield, next we want to talk about what can be done with that windshield for better cold range performance in electric vehicles. So defrost in an electric vehicle, or even in a combustion engine, uses a lot of energy. We flood the surface with heat. And this uses 3 to 4 kilowatt hours. It's really not a problem when you have the combustion engine and all that free source of waste heat. But in an EV, you have to pull energy from the battery in the vehicle, so you're taking away from range. And this is quite a bit of heat for defrost. In addition, defog is also a problem, probably larger than in gas engines. Drivers turn down the heat to conserve range. We've done surveys of EVs drivers, and they've commented on this. And also we're seeing is the vehicles are being sealed more tightly to reduce NVH, because you don't have that gas engine. They're more tightly sealed, and so you get more fogging up of the glass surfaces. And defog is also energy intensive. There are current heated windshields out there today, and these have been around for a long time. So this is not a new technology. There's wire resistance technology. It really doesn't offer much in terms of solar gain reduction. It does have a problem if it does reflect light when you have concentrated light sources behind it, especially at the beginning and end of the day. And these are typically powered with 12 or 24 volts. It's a boost heat system. It's not replacing defrost. And this is the same technology also that's in the rear glass. Low E glass, mentioned this was developed for the flat glass market, and you are seeing this in EV windshields. Also, many Class 8 trucks already offer this in North America. These are typically heated with 12 or 24 volts as boost heat, and it's not replacing defrost. So what I want to talk about today now is another way of thinking about providing higher levels of voltage and power to get better thermal performance that can potentially replace and remove the defrost and defog that comes out of the HVAC system. And we're going to do this, and the idea for this comes actually out of the Dartmouth College of Engineering ICE lab. There they studied how ice forms, the way it adheres to surfaces, and the most efficient way to remove it from surfaces. And the key insight, and this was a physicist there who was really studying this at a first principles level, was looking at only allowing heat to reach the interfacial layer of ice that's shown in that red band on the right side, that quasi-liquid. So that the heat melts, creates an interfacial layer, or melts it, you get a thin layer of water, and then the ice can quickly be removed. And the best way to do that was pulsing energy in a way that keeps it right at the surface and doesn't go any further than, let's say, 1/10 of a millimeter where that interfacial layer is. We want to show a video of our technology on the left side. and a standard HVAC on the right side. And as you look on the left side, you're going to see the it go from opaque to transparent very quickly. That's the interfacial layer melting. And with current HVAC systems, what we're seeing is that hot spot in the center, and then it's slowly moving out. If we look, this is after 16 minutes, but you have this area where it's completely melted. You have interfacial melting here. That's where you have a thin film of water on it, but where it's opaque, that is still bonded onto the glass. So you can run the wipers all day, but you're never going to remove that until you at least get that interfacial layer melted. So the current ways of transferring heat, you have all these heat transfers, you have it all directed to a very concentrated place on the glass, so it's not evenly distributed for the heat. It's just very inefficient. And so using that transparent metal layer that's in the glass to be the source, you get this even source of heating that can defrost FMVSS 103 in 1 minute. And so their controller that we develop are connected to bus bars that are in the windshield. We have one algorithm for defrost and one for defog, and this uses about 20 times less energy than an HVAC system. And when we've done testing in the lab, this is FMVSS. We're using about 20 times less energy. It's compared to 4.2 kilowatt hours. We're typically using 0.2 and oftentimes in the low 0.1 range as well. We've also tested this down to minus 40 C at the Ontario Technical University's ACE climatic chamber in Oshawa, Ontario. And at minus 40 C, we've removed a 0.5 millimeter and 1 millimeter of ice. What's really interesting about this, if you look at the amount of energy to be removed at the two different amounts of ice at the different temperatures, you'll see the energy is almost identical. And that is a sign that our technology is working, that the heat is only reaching that interfacial layer. So we have other tests where we show the amount of energy necessary to remove the ice is not dependent on the thickness of the ice at all. And this demonstrates that. We've also done comfort tests. This is how long does it take a vehicle that starts at minus 20 C or minus 10 C to get up to minus 15 C. We've done this for both defrost and defog. In this case, we're showing the defrost results and the time to reach plus 15 C. And it's about a 50% reduction in time to get from minus 10 C or minus 20 C all the way up to plus 15 C. And what's happening here is more heat is being directed into the cabin rather than diverted up to the windshield. So this is more passenger comfort, faster from a cold start. Now talking about defog, we've interviewed EV drivers and asked them questions about their behaviors. And one of the things that's most interesting is that they do turn down the heat to conserve range. And when they do that, what ends up happening is you get more fogging up of the glass, and drivers are noticing that. So when we test to defog, in this case, this is a dynamic test at minus 20 C at 100 kilometers per hour. This shows the energy reduction compared to the HVAC system that was in the vehicle and our energy that was here, a 61% reduction. Also, when we did a comfort test, starting from minus 20 C going up to plus 15 C, was 33% less time from minus 10 or 20% less time from minus 20. Again, this is a way to get more heat into the cabin instead of applying it to the glass. And this chart here starts to look at thermal efficiency for both summer and winter. So on the left side, this shows the different conductive layers that I talked about that are used in low-E glass. And then if we look at different voltages that are compatible with the metal layers, we've measured energy that's to defrost to FMVSS 103. And you can see the time is shown in the next column. And then what is the TTS for these different metal layers, and then what is the thermal efficiency of the heated windshield using a system like ours. And so you can see that as thermal efficiency that gets much better as higher voltages are applied to the glass, and it improves quite significantly. And the thermal efficiency goes quite a bit down if you don't if you don't use pulsing or modulating the way the power is delivered to the windshield. But this is a good way to think about some of the trade-offs in terms of the different coating technologies for the windshield versus the potential thermal efficiency that's possible. I'll also note that the coating technology is improving and will narrow the trade-off. Either let's say, very good solar transmission or TTS values of, let's say, 40% that triple silver offers. The thermal efficiency in wintertime is lower. But if we look at the bottom of the chart, something like fluorine tin oxide can offer very high thermal efficiency, but the TTS is lower at 60%. Or the solar energy gain is higher at 60%. Sorry about that. Also want to talk about the implications for electrical safety. If we think about ISO 26262, it's very important that we are preventing human exposure to higher voltages during the operation, assembly, service, and accidents. And there's 6 different controls here that can reduce that exposure in an electric vehicle. And these include checking to see if the system is connected to the windshield, doing a resistance check to see if there's any system damage. That would include damage to the windshield. Current limits, capacitance check, also checking or shutting off during service, or shutting the system down in the event of an accident, whether it was another car or pedestrian. There's some significant value propositions for the driver. You can extend range in both summer and winter. There's higher perceived thermal comfort from creating a heat shield around the driver and keeping the vehicle cooler in the summertime. You have faster morning startup. This is important for commercial trucks, which are largely parked outside. And then another interesting potential for eliminating air defrost and defog is the ability to eliminate the causes of dry eye. This is very important in commercial trucking and for fleets. There was a study that came out last year where they tested commercial drivers, and almost 25% tested positive for a medical condition, dry eye, where your eye is not able to generate enough moisture, and it creates a number of other problems. But in this study from the American Academy of Ophthalmology, they point out 3 of the main causes for it, which are low humidity, high wind speed, high temperature. And that's exactly what air defrost and defog does in the wintertime. When I've talked to snowplow drivers in the past, they talk about this as being one of the hardest parts of their job, is having to operate with the defrost on max while they're plowing for long hours at one time. The stress on the face and the eyes from this low humidity, the wind speed, and the high temperature really creates a lot of challenges for drivers in those conditions. So in summary, EV range is severely limited in warm and cold temperatures. Showed a couple of the different studies that are out there that show that. And the further you get away from ambient temperatures, the larger these impacts are. Low E windshields can have a big impact in warmer temperatures. They can reduce up to 60% of solar transmittance while maintaining that visibility transmittance above 70%. And it can have a significant impact on lowering cabin temperatures in the summertime. And the low E glass has already high penetration rates in residential and commercial. We're seeing increasing adoption in electric vehicles. Fourth, the existing heated windshields are mostly boost heat systems using 12 and 24 volts, and these are far from thermal efficient and cannot replace defrost or defog. As we have more options to tap into higher voltages like 48 volts, we can get higher thermal efficiency that leads to lower energy consumption and greater EV range. And these can completely replace the HVAC, defrost, and defog functions while keeping the HVAC system there for cabin heating and cooling. So at this point, I think there's some very interesting trends that are happening and offer some significant potential improvements going forward as we think about some of these different issues affecting warm and cold temperatures. At this point, to take any questions and maybe look forward to taking any of those now.
All right. Thank you, Derek. We do have a couple questions from the audience. Before we get to those, got a few questions that I'd like to run by you. The first thing I want to say to the audience is Defrost will be presenting at the SAE Thermal Management System Symposium, TMSS, in October. So if there's any additional information or feedback that you'd like to give them, that you'd like to see at TMSS, please take the opportunity to do that here or by email, what have you. But certainly in the chat here would be great. Okay, just a couple of questions to get us started. Derek, how is architecture changing, and how does this impact the heated windshield?
Sorry, what was that again, Dwayne?
For you, Derek, how is architecture changing, and how does this impact the heated windshield?
Yeah, so I've been in automotive for more than 25 years, and there is a lot changing right now. Probably the largest change relates to the voltage, the high voltage architecture, and we see a lot of interest right now. I think some of this coming from Tesla's recent announcement about moving towards 48 volt systems for certain levels of current. We see more interest, I think, in higher voltage systems. I think up to this point, it's been assumed that we can't do high voltage in other places, but I think there are ways. The glass, being a natural insulator, does a lot to be able to protect it, and there's ways to detect any type of changes in that surface that make it easy to detect if there was a problem like a chip or a crack, especially if it were to penetrate the metal layer. There's definitely a lot of changes going on right now, and I think the biggest one relates to changes in the different ways of getting higher power or voltage levels than 12 volts.
All right. And how do you see this system being integrated with the windshield, the HVAC, and the ECU controlling the climate control system?
Yeah, so we're not a glass maker. We're not in the coatings business. I think the glass makers are well established there and understand that technology. very well, and most of the OEMs do as well, especially I would say a number of the ones in Europe that seem to be further along with putting low-E windshields into vehicles. The only difference they have to do is put a bus bar on the sides of the glass that we connect to, and generally, we are developing controllers for prototype and demonstration purposes, but the OEMs have existing electrical control suppliers, and we believe that we can help them spec that. But ultimately, what we want to do is be able to provide control on let's say a microcontroller or on a chip that would then go into a climate controller or body control module that would be able to interface with a power controller that delivers the energy to the windshield.
All right. What's it like working with OEMs and tier ones as a startup?
Yeah. Well, first, I'll start with our involvement with SAE has been very helpful in that regard. Last year, we won the Gamut competition at World Congress. That's the Global Automotive Mobility Innovation Challenge. And that gave us some very good exposure to OEMs and tier ones. We also have exhibited at World Congress, and then we have opportunities for further presentations, like Sammy will be making one at the TMS, the Thermal Management System Symposium, TMSS, later in the fall. So these have been good to open doors. And the other thing too is I think it's important that we're flexible around the way that we go to market with the solution. Yes, we're designing power controllers, but we don't feel we need to own that. We feel there are other people that can do that. There are a couple areas that might have to be a little different than what's done today. And we're trying to show OEMs and tier ones how to do that quickly and efficiently, but we're flexible with that part. There's other players that probably can deliver that piece. So probably our role, even though we have a lot of interface with OEMs right now, I do expect ultimately we probably will become a tier 2 supplier to a tier 1 is probably the best way to make this work.
All right. One more from me, and then we'll get to the audience questions. How many OEMs and tier 1s are you currently working with?
Yeah, so for automotive and truck OEMs, there's probably about 6 that we're at various levels of discussions with. 2 of them we've engaged with on paid development projects, and there's about 6 tier 1s that we're at various levels of discussions with.
All right, getting some interest, so that's great.
Yeah.
All right, so questions from the audience. First from Bill Shellman. Is Defrost currently working with windshield suppliers to adopt this technology, and who is responsible for the defrost or defog performance between Defrost and the windshield supplier?
Good question. So yes, we are working with a number of the glass makers and have developed, let's say, custom solutions for POC trials with OEMs, and even we've done some for ourselves. What I do like about it is I think we have a shared interest in promoting the benefits of low-E glass for better range performance. I think the windshield's performance is for the summer, and our solution is for the winter. So it's not, we're not really competing in that area. Yes, there are some heated windshields, but I think most of those have been focused on the lower voltage applications like 12 and 24 volts. So our relationships in that regard have been good. And I think the second part of the question, remind me of that one.
for the windshield?
Oh, for the defrost performance. It's tested by both the glass maker and the HVAC maker. For what we're doing, I think it aligns more with the HVAC side, but at the end of the day, it's a system test of all of those things. So we do FMVSS testing here in our tech center here in Oakville. But we also know that our windshield and glass suppliers can do this, as well as the HVAC makers and the OEMs. Ultimately, I think it really comes down to a system performance. And I really think it's shared. What we do like about it, though, is it's a standard test that when we're talking to automakers or tier ones here in North America, Europe, or Asia, everybody understands that test. There's no variance. On the other hand, defog is a little bit more challenging. It's a little bit more subjective, and there's not one single test there, but at least defrost, there's a common standard, and it makes it easier to have a baseline when we present results.
All right, and certainly, ultimately, the OEM is responsible for defrost performance, but you guys have to provide the tools to make that happen between you and the windshield maker.
Yes.
All right, question from Mike Bondi. Can the system work with polycarbonate windows instead of glass? Good question. Yeah.
Yes, that could almost be another topic there. So here I'm showing transparent conductive materials that are well established in glass materials. But we've been very impressed with some other polymer materials, one of them being carbon nanotubes that can work in polycarbonate surfaces as well. So we're excited to see another potential application beyond just the glass systems, but also plastic surfaces that are typically covering cameras, LiDAR, and other things, and the LED headlamps that can't generate enough heat.
All right. Yeah, interesting. I wouldn't have thought of that. So good question from Mark.
Yes.
A question from Alan Leopold. Had to walk away for a minute during the operator comfort slide. Go back to the operator comfort slide, and how is heat transferred to the air?
Which slide was that?
Operator comfort slide. I think it was the one with the picture of the vehicle interior. That one too. Yeah, either one. Yeah, that one.
So here we're comparing we're looking at we're measuring the time that the cabin with all these different temperature sensors reach 15C with two different tests. One is the baseline test, just using so if we look at the defrost button is set to max heat and max blower. And then when we come for the comparison test, the defrost button is off. There are vents that are on, and then the max temperature is directing all the heat into the cabin. And so then we're comparing the time it takes for the vehicle to reach plus 15C. Is there anything else you want to add?
No. So the heat still goes through the air for the normal HVAC for the cabin comfort, but we're not using that air for the defrost function anymore, because the defrost function can do that.
So it's basically, rather than the HVAC system having to heat two things at the same time, the glass and the cabin, we're taking over the glass heating so that the HVAC can direct all of the power, all of the energy into the cabin. And that's why you get a faster time to 15C or cabin comfort.
All right. And three questions from Chris Michalowski. I'll start with the first one. Do the coatings change the color of the windshield?
From what we've seen, no. There is, I would say to the casual observer, no, but I think the glass makers probably have more detailed analysis of the optical properties of it. When I look at, I can't tell if Lowy is in there, but I'm not doing the correct optical tests for that.
So in your estimation, it might, but not in a dramatically noticeable way, like maybe some of the gold windshields we saw in years past, things like that.
Correct. Some of the work that Southwall has done is looking at that. Is some of the in their study they do talk about the change to it, but I can't notice it when I look at the glass. But they do get into some of the analysis of the optical property changes related to color.
All right. Next question from Chris. Will windshield with low E coatings create electromagnetic interference? And then I'll add to that, will pulsing electricity through the windshield create electromagnetic interference? So either the low E coatings or the pulse electricity, any EMC type issues?
Yeah, so we've tested our system to CISPR 25, which is the general standard for EMC, and we've also tested to an OEM's EMC, and we passed CISPR 25 to class 4, and we passed the OEMs all of their EMC requirements. But we do add EMI filtering in our solution to achieve that. The glass does. It can create some challenges there, but my understanding is there are different ways to ablate the glass or create cutouts to enable it to pass through. I think they have a lot of experience with this in trains and buses, where low E glass is almost used exclusively, and you can notice that you don't have a problem with cell function inside of trains for that reason. So I think it is something that has to be managed, but I think there's ways that the glass makers are able to do that.
Okay, so you're thinking about it from a like a cell phone reception type of situation, things like that. Okay.
Yes.
How about things like radio interference, things like that?
On radio interference.
No, I mean, that's what we see on CISPR 25 testing. So there is ways to manage this and prevent any significant interference coming from the windshield itself. Of course, the electronics could be done, but the windshield itself, there is ways to manage that. Yeah.
All right. Okay, last question from Chris, and last one from the audience, unless somebody else has something to add. We do have about 15 minutes left if anyone else has any questions. But the last question we have right now, will windshield with coatings affect function of sensors in the windshield, rain sensor, radar, camera, LiDAR, those types of things? How do you deal with that, and will the coating in the windshield prevent an issue there?
Depending on what, so right now, for the low E windshields that are out there, they're already working with that or working around it. What we've noticed is typically there may be a cutout that's trapezoidal shaped right at the top to allow anything that might have any problems with passing through this transparent metal coating. That's, from everything we can tell, that's fairly straightforward to work with.
Any questions? You can contact the SAE Detroit section at the email shown here, or at Defrost. Thank you everyone for joining today. And if there's no other questions, comments, anything from Stephanie, we'll go ahead and I'll close the meeting. Thank you, Derek. Thank you, Sammy, for joining us today.
Thank you all very much.
Thank you.